Next, we're going to move into the concept of binary trees. One of the problems that eliminates is this idea of having a set maximum number of elements. If we only have a maximum of 2 children, then we can express the 2 links, the 2 node links, as discrete variables. We're going to have the left child and we're going to have the right child. But let's get on to some terminology here. If we take a look at this tree, you can see it is binary in that every single node has a maximum of 2 children. You can have 0 children, you can have 1 child, or you can have 2 children. So that maximum of 2 different elements as children determine this to be a binary tree. So with this then, we would have some special terminology, and they really are kind of using that analogy or that metaphor of family relationships. So for example, A is C's parent. I guess we have been using this a little bit because it's pretty clear. So the parental relationship is when you go up the tree just one link, and then you have one parent, in this case, one parent for each of the nodes. And then the parent can have up to 2 children. So we'd say Q is C's child. Okay. Now we can do a couple of things. We can start to talk about grandparent. So if you go up to, you could call that a grandparent. That is not all that common. But you can also talk about ancestors. So for example, one of X's ancestors is Q. Or you can say for J, L is J's descendant, here a grandchild, but that there's something down the tree, well, any of these in that subtree would be a descendant. Okay, so we've got ancestors, descendants, so we got ancestors and descendants. And then what we can do is talk about whether or not there is a path. Okay, now all of these are technically connected together, but when we talk about a path, we mean where you're only going in one direction. So there is a path from A to R because down, 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 there's a path between A and R, and there is a path between M and R. There's a path between H and A, and there's a path between Q and L. All those are paths. But we would not say there's a path between M and X because you'd have to go up and then back down. So connected edges and the criteria is in Fritz's favorite band, One Direction. In one direction. So in one direction, we can only go down, 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 or up, up, up. So that would be a path. And the depth of a tree we can talk about the depth of the tree. We could also talk about the depth of a node. So the depth, let's start talking about the depth of a node, is how far down from the root, and the root has depth level 0 in this case. So we've been talking about it. Let's go ahead and label this. A is going to be the root node in this case. So we have A as the root, and it has a depth of 0. So Q has a depth of 1, R has a depth of 0, 1, 2, 3. R has a depth of 3. And we can also talk about the depth of a tree. And that is depth of deepest node. In this case, the depth of this tree would be 0, 1, 2, 3, 4, 5. So it's got a depth of 5. And then just to make it weird, they have the concept of the height of a tree. And that's just depth plus 1. That means you count. It means you count all of the elements. So that's the depth and the height of the tree. Okay, so that's with a binary tree. And these are just some of the terminologies that you'll end up getting. Now for a binary node that we would call a bin node, we're going to draw it, well, we're going to draw it as circles, but if we think about what needs to happen, today we're going to be dealing in the in-class exercises with characters. So I'm going to put a B inside there. And so then this is going to be the left and the right. Okay, these are going to be internal variables. Now, if our class is called bin node, then this is going to be of type bin node pointer. That's the type. And this is going to be of type bin node pointer. Okay, so those are going to be member variables, and then this is going to be the payload. Maybe it's going to be called data, but it's going to be of type char. So if you think about that, then when you have your private section for your member variables, you may have something like bin node left and bin node right, and then the payload is a char. Okay. What else are you going to have for a bin node? You're going to have a constructor. And you need to have a default constructor where this will be null, and then you choose probably the null character, which is 0, for this by default. And then for this, you're going to have a get left and set left. So you'd have a get left, set, get right, get set left, get right, set right, and then get data, set data. But all of those will be very simple. This is a structure that should be remarkably familiar to you. Remember that we just got done working with the double-ended queues, and we had the D-link. So the D-link was essentially the exact same thing, only we called it forward and back, next and prev. Here we're calling it left and right. So actually the underlying mechanism of a binary tree is very similar to a D-link. It's just that we called it left and right as mnemonics, and we might have a different payload. But this will work the same, only with a doubly linked list. We usually have something like, it's meant to be kind of chained together linearly, whereas the tree, well, the tree then we're just going to bind and chain them together this way. So if you needed to make a manual tree like this, you could declare discrete bin node variables for each of these. Then you'd have to set the letters for each of these, and then you'd have to set the children. So you'd say like on the L link, L set left M and L set right X, and then you have this portion of the tree. Now notice that any given bin node itself is actually a tree because it's going to be the start of a tree that goes down. Now it might be a small tree or it might be just a single element, but notice as we go through here, if I would grab just the J, if I just grab the J, well, if you give me a reference to this J, I can find all of these other elements within the tree. But just the bin node itself forms a tree on its own, forms a tree structure. Now, it doesn't have any extra useful things, but it represents and holds the information for a tree. Likewise, if I just grab the C, well, that's not a very big tree, but it's technically a tree. Or if I looked at just H, Well, H is a tree, it's just not a very interesting one. So this recursive nature is going to be pretty important as we go along.